So, welcome, friend. I'm going to teach you non-ferrous metals. Yesterday, we discussed about the ferrous metals. As you know that there is great importance of the ferrous metal in the construction industry. At the same time, non-ferrous metal is also has its position in construction industry, and we have a different type of the non-ferrous metals. It includes the aluminum, copper, zinc, lead, tin, nickel. These six metals is heavily used in construction as a non-ferrous metal. If you look at the production of non-ferrous metal, is very small. Is very small if you compare it with the iron. And as you know that the iron has its importance in the engineering structure and industrial uses. So obviously it has the higher production compared to the non-ferrous metal. Now moving to the is commonly used non-ferrous metals, that is aluminum, tin, copper, zinc, lead, and manganese. Let me start with the aluminum. The principal constituent of bauxite. Bauxite is a mineral that is available on the surface or beneath the surface of the earth, uh, and its composition is L2O3 twice H2O. This is the hydrated version of the alumina. So the principal constituent of the bauxite which yield aluminium on a commercial scale are hydrated oxide of aluminium and iron with some silica. Some of the other aluminium ores are corundum, this is the one ore, kaolin is also known as the China clay, and creolite. The ores are used as a raw material to produce the aluminium. How we produce the aluminium? The ore is purified by Byers process and is reduced to aluminium by whole Herold process in two stages. These two stages include the first stage, bauxite is converted into the alumina by how we convert the bauxite into alumina, that is L2O3, by roasting, grinding, heating with sodium hydrate and filtering. Then it is agitated for several hours to precipitate the hydrate, which is separated, washed, and calcined at 1000 degrees centigrade. In the next stage, aluminum is extracted by electrolysis of alumina in a molten bath, that is given in the figure that we will discuss, of cryptolite, a fluoride of alumina and sodium. A flow diagram for the extraction of aluminium is shown in the figure 14.2 that we will see. So aluminium is a silver white in color, as all we know, with a brittle metallic luster on freshly broken surface. It is malleable, less ductile. It is malleable, less ductile than the copper, but excels zinc, tin, and lead. Aluminium is harder than tin. It is, remember one thing, aluminium is harder than tin. Aluminium is very light, soft, strong, and durable, and has low thermal conductivity, but is a good conductor of electricity, and that is why it is also used in the electric appliances and manufacturing of the wires. Aluminum can be riveted and welded. See, this is the very good property of aluminum. You can rivet. I think that is well understood. If you want to join two plates, then you have to insert the rivet, right? You have to drill the hole and you fix up the rivet, right? This is called as the lap joint. That can be done in the aluminum, and even you can do the welding, but cannot be soldered. Yes, copper can be soldered, but aluminum cannot be soldered. It can be tempered at 350 degrees centigrade, and melting point is 657 degrees centigrade. It has a good tensile strength of 117.2 Newton per mm square, and in the cast form, and 241.3 Newton per mm square in when drawn into wires. So when you convert the aluminum to wire, see there is an increase in the tensile strength. Increase in what is tensile strength? Tensile strength, if you have a rod, if you apply the both hand with some force, that is tensile force T, then there will be a increase in the length of that bar, right? And the load will be divided in the this area, right? This area, and the load, that is T, is divided per area, that is what called Newton per mm square, and that is what called as the tensile strength, right? Tensile strength. Aluminium is found to be a resistant to the attack of nitric acid, dissolves slowly in concentrated sulfuric acid, and is soluble in hydrochloric acid. So this is the adverse property of the alumina. It reacts with the nitric acid, it reacts with the sulfuric acid, and it is soluble in hydrochloric acid. So you cannot use this aluminum where there is a acid exposure. At the normal temperature, it is not affected by sulfur, carbonic acid, carbonic oxide, vinegar, seawater, etc. But it's rapidly corroded by caustic alkalis. Yes, this is a big challenging property, adverse property, rapidly corroded by the caustic alkalis. So wherever you have the caustic alkali exposure, you should and not use this aluminium at all. Now see here the extraction process, extraction of alumina by electrolysis. Uh, so the fused light plus L2O3 is put over here, and the molten aluminium is at the bottom. It will collected here. Now this is the carbon lining, and when these linings is having some charge, and these are the electrolytes, and which is covered with, when you just have the power in this uh, electro, and due to that electric conductivity, this aluminium will be come out, right? It will be melt, right? And it will be separated at the bottom, and that will be taken out. This is called electrolysis, similar to the you do the hydrolysis, that you put two bars and you give positive and negative in the water, so there will be a O2 and hydrogen will be come out. So this is something like that, and this is the hoop cell by for refining the aluminium. So here you use the graphite electrode, and you import the aluminium over here, and when you charge, positive charge it with, and this is the negative charge. So what happened in the presence of this, the fluorides will be at the mid of this solution, and impure aluminum will come at this precipitate at the bottom, and the carbon lining is done over here, and you will get the pure aluminum that will float over the this pan, right? So this is a hoop cell in which you purify or refine the aluminum. This is the flow chart of how to convert the ore into the our aluminum, molten aluminum. So first of all, we do the grinding of ore, then we add the caustic soda solution into that grinded material, then dissolve aluminum solution, then removal of impurities that you have seen over here, then water removal that is done in the clean, then electrolysis that also we had seen here electrolysis, and we got the molten aluminum. Now there are some alloys, means that aluminum is commonly alloyed with copper, silicon, manganese, magnesium, zinc. We do this alloyed with the aluminum to improve the mechanical properties, to improve its mechanical properties. Some of the aluminum alloys also contain one or more of these metals like manganese, lead, nickel, chromium, titanium, beryllium. A large part of the aluminum production is utilized in making light, stiff, corrosion resistant alloys with this metal. So, why they are adding to have the very lightweight, stiff, corrosion resistant alloys by adding this type of the metal into the aluminum. So that added inside this aluminum to get this type of the properties. Aluminum alloys may be classified into class. First, that is a cast alloys, which are shaped by casting. So it means you melt the alloy and then you cast into the mold, right, into the mold, you pour it into the mold. That is what called as the cast alloys. And another one that is called as the wrought alloys. Now wrought alloys is worked into different shape by mechanical press. As we have the rolling mill and all that thing, we are just rolling. We have the rolling rollers, and we put the plate inside that roller, and then we get something that is what called as the rolling, and it is worked out by mechanical means. Now, the cast alloys are generally binary alloys containing copper or silicon and sometimes magnesium. Wrought alloys contain copper, magnesium, silicon, manganese that from the precipitation hardening alloys with aluminum. Following are some of the aluminum alloys. This is a duralumin, this is a mangalim, aldural, Y alloys, and that is the aluminum alloys and aluminum bronze, then light alloy, then aluminum copper alloy, aluminum zinc alloy, aluminum silicon alloy. So these are the alloy. It differs as per the contents. Duralumin contains 3 to 5% copper, 0.51 to 1% magnesium, 0 to 0.07% manganese, 0 to 0.3 to 0.6% iron, and 0.3 to 0.6% silica are present in the impurity, present as a impurity. This relative density, the relative density is 2.8, which is quite low as compared to that of mild steel. However, when rolled and heat treated, tensile strength equal that of the mild steel. So when you give the heat treatment to this alloy, you will get the tensile strength is equal to the mild steel. That is 200 and yield point. It is 206.85 Newton per mm. It's quite good tensile strength. It is highly resistant to corrosion. Wire and sheet are drawn from duralumin, right? Whatever the wire you are getting, that is duralumin. and duraminine may be fabricated into different structural shape to be used for the construction. Similarly, we have the different type of these alloys which has the differed content of the impurities and it has a differed properties. So you are requested to just read these alloys and what is the content of the impurities and what is a difference between the physical and mechanical properties of these alloys and its respective use that you have to learn by yourself. Now we move to the copper, that is another metal, and copper is extracted from the ore similar to the our aluminium. What are those ores? That is copper pyrite, then such as the chalcopyrite and malachite and copper glans. These are the commonly used ores, right? And done as per this roasting of copper pyrites ore in reverberatory furnace, the reverberatory furnace. Nearly all the coppers is extracted by smelting. This is the common process, that is smelting. After calcining the ore, it is mixed with the silica and coke. Calcining means we add the calcium carbonate. Then it is oxidized in the Bessemer converter where removal of major portion of iron and sulfur compounds is affected. The crude copper thus produced is known as blister copper. Yes, crude copper is known as the blister copper, which is cast into small pigs, right? Into small pigs. The blister copper contains many impurities and is refined in reverberatory furnace. Finance, it is a furnace, right? It is a furnace. And by electrolysis, as you seen in the aluminium. We are not going into much detail of this processes. We concern about the properties and its use. What are the property and where we will use this particular material. So we just know that what is the brief, how it is derived, how you are having, how you are processing these particular metals. So copper, as you know, it is a bright shining metal of the reddish color. And yes, one more thing, when this copper is in the moist weather, it converted into the greenish color, right? The copper is converted to greenish color when it is in the exposure of the moist weather. Copper is malleable, ductile, and can be worked in hot and cold conditions. It is not weldable, but you can do the soldering, except the red heat. It is soft and good conductor of heat and electricity, and that is why we are using it for the electric wires. Uh, the electric resistivity of the copper having less than 0.1% of non-metallic impurity lies between 0.155 to 0.159 ohms per meter gram at 20 degrees centigrade. The resistivity increase with the content of impurities. Yes, it is obvious that if you have the higher impurities, then the resistivity will be high. With amount of wire drawing, its tensile strength is high. Now, use of the copper. Copper is extensively used in the electric purpose, tube, for condenser. Yes, if you see the refrigerator and the AC pipelines, these are the made with the copper. Even in we are using it in the electric wire. So, in the building, copper is used for the roofing, seating, and dam proofing. Its use is restricted in appliance and connections used for the water supply. because you know that it reacts with the water that we have seen. When it is exposed to that water, it become a greenish, right? And that is what the problem. Now alloys, alloying element most frequently used with the copper are. Now as you seen in the aluminum, we are adding a different metals. So here we are adding zinc, tin and lead. Some of the important alloys made with the copper are brass and bronze. Bronze medal, you have heard about this bronze medal. That is, yes, exactly, it is a bronze. And brass. Brass is a alloy 60 to 90% copper and 10 to 14% zinc. So it is a combination of copper and zinc. And the color is silverly white for low content of copper and copper red for high copper content. Brass may be either cast or wrought. Brass is casting. Brass for casting usually contain 30 to 40% zinc and tin 2 to 3% when added increase the hardness but decrease the ductility. Addition of the 2% of lead render brass easy to turn, file and polish, but ductility and strength are reduced. Aluminium 1 to 6% when added raise the strength but decrease the ductility. Cast brasses are stronger and more ductile than either of their component, copper and zinc. Compared to copper, its electric conductivity is quite low. Zinc content 37 to 45% for brasses suitable for the forging, rolling, or extruding and hot working. These are the words which are used uh, in the industry, in the manufacturing of the machinery. Brasses used for extruding contain 2 to 4% lead to make them flow easily through the dies. Dies means if you want to have the something that you prepare the die and you pour the material inside and you will have such a mold. So that extruding contain 2 to 4% of lead to make the flow easy in the die. Lead, however, lessens the amount of reduction in the working, which these alloys will withstand without cracking, makes the metal more susceptible to burn during the melting. The brasses brought in a shape by cold working have copper to zinc ratio 2 to 1 and 3 to 1. The former being used for making seats, wire and stamped and drawn articles. 3 to 1 copper zinc ratio, that is 3 to 1 for this type of the so brasses copper to zinc ratio 1 to 1 used for bronze brass wood, brazing brass wood. They have a very high crushing strength but are too brittle for mechanical working. Then yellow metal, that is also alloys containing 57 to 63% copper are called months metal, also known as the yellow metals. These are used in making bolt, rod, tubes, extruded shapes. Alloy having 70 to 75% copper are used for making the cartridge case, condenser tube, spinning operation. With 80 to 85% copper, the brasses take a good polish, resembling gold, and are used for making the pendles and artificial jewelry. So, your artificial jewelry, that is what your 80 to 85% copper brass. Then manganese bronze and naval brass, then stereometal, delta metal, and the bronze. So you there is only change of the zinc, right? That is a change zinc, iron. The constitution are on and the proportion and the constituent of this alloy is different, and that will differ these metals and alloys, right? And its physical mechanical property uh, that will totally change, and it will also change the then zinc bronze, phosphorus bronze, lead bronze, and copper beryllium alloys. Then we go to the zinc. Main source of zinc is a sulfide ore, right? Sulfide ore is a main source of zinc, land and blackjack, blackjack, right? Blackjack. So blackjack contains 67% of zinc. The other ores for extraction of zinc are zinc carbonate, calamine, that is ZnCO3. It contains 52% zinc, and zinc silicates, hemimorphite, and this velimite. These are the ores which are used to have the zinc. The sulfide ore is finely ground and calcined with the reverberatory furnace until nearly all sulfur is expelled. Carbonates ores and silicates ores are often calcined in the shaft furnace before being distilled. So here you have the vertical retort furnace for extraction of the zinc. So you put the charge over here and you blow the gas and air from this nozzle or this opening. It will heat up this whole cell, and the burned gases will come out. So that will be move around this and it will come out from here. When you put this charge will uh, settle at the bottom, and the producer gas is also inserted. Producer gas is also intaken here, and due to that you will have a molten zinc that will flow in this way, that will travel a lot, and there will be water vapor. So this is the process of how to have this. You just read this process, right? We are not much bother about the this type of the processes. We are bother about the properties and use. Zinc so cast is known as the splatter, right? This is called. There you could have the understanding of how the that is been prepared. So the most important property of zinc is its resistance to atmospheric corrosion. This is the biggest. See, corrosion like a cancer. Ductility is good and it can be deformed in desired shape. Lead less than 0.1% make the pelter roll easier. However, its option weaken and ductility is reduced. Iron and cadmium embrittle and harden the zinc are therefore determinant in the pelter, which is to be rolled or used for the galvanizing. This should not be exceed 0.02% zinc, either rolled or cast. Right. So, and the use that is produce brass, German silver, some of the bronze. So we are using it as a alloying, right? We alloyed with the copper and aluminum, and we are getting these things. Then boiler tube, fruit jars, covers, can, yes, can. That is also we are using the zinc can for resisting the corrosion and for negative pole piece of batteries. Then the lead, yes, lead. We have two process here, so you just read this process. You put the charge here, then you have the air you are blowing from here. This is the coke, and this is the ore and lime, ore with the lime, and you will get the that particular thing, right? And roasting is done, and then that roasted material is uh, used for further processing. This is melting of the galena in the blast furnace. This is the melting process. We are not bothered about the exact procedure, but you just read everything. Um, be concerned about the property. The pure lead can be scratched even with the fingernail, highly malleable and can be rolled into thin foils. It has a blue-gray color and dull metallic luster when freshly fractured. When exposed to the moist air, it loses luster due to the oxidation. Relatively dense Relative density is 11.34 and melting point is 327 degree. Softness and specific gravity of lead are reduced because of the impurities such as antimony, arsenic, zinc, copper, magnesia raises the hardness abruptly. Now, what is the use? It finds its principal use in paint. See, we use in paint as a base, lead pipe, and joint in sanitary fitting and in battery. Yes. These are the use of that lead. Some of the important lead alloys, right? Lead antimony alloy. Again, same. Change in the percentage, right? Change in the percentage, and there will be change in the mechanical and physical property. So lead antimony alloys, also known as a high lead alloy, and it has alloying 15 to 20% antimony with the lead. Antimony serves as a hardener, and alloys so produce is used for making bearings. Lead antimony tin alloys contain 10 to 20% antimony and 5 to 20% tin, and the remainder lead are used for the bearing subjected to moderate load. Mongolia metal. Mongolia metal is one of the common bearing metal of this class. These are also used for type type. Then lead tin alloy, then fusible alloy, right? And that is having the different use. Then we have the tin that it is extracted from the black oxide of tin. Cassiterite and tin is extracted from the ore by crushing, roasting, melting to temperature of 1000 degrees centigrade in a way similar to the copper. Now we go to the property. Tin is silver white, lustrous, and extremely malleable metal. It is so soft that it can be cut by knife. Yes, you can cut it by knife. Its specific gravity is 7.3 and melt point is 232 degrees centigrade. It is hardened and more ductile and strong than lead. Tin is as ductile as soft steel. It is highly resistant to corrosion and has low tensile. High resistance to corrosion and low tensile. This is the very crucial property. Use, where we will use seat coated with tin are used to make cans, tensile and furnace pipes. Seats coated with the lead tin alloy are used for the roofing. Tin is also used for making the bronze and other alloys. Now we look at the alloys of this tin, that is solder, bebit metal, then white metal and pewter. So solder, it is obtained by alloying tin with antimony, lead and tin. These have low melting point. Solder is used for joining copper, lead, tin, iron. So we use it in the soldering, right? Then bebit metal, these alloys with tin base containing small proportion of copper and antimony. This is used to making the bearings, right? And white metal, that is also used for making the bearings, right? Making the bearing. And pewter, it is alloy with the 75% tin and 20 to 25% lead, and it has a high corrosion resistance. Now we go to the nickel. Nickel is generally extracted from the pyrites and silicates. So here the particular process is not given how we are extracting this nickel. So properties: brittle metal approaching silver in color. Nickel takes good polish and at ordinary temperatures does not tarnish or corrode in dry air. It has specific gravity 8.3 and when cast, and 8.7 when it is rolled. And the melting point, see, it is very high. It is 1500 degrees centigrade. It's almost a hard as soft steel, far more malleable, and when rolled and annealed, in somewhat stronger and almost ductile. Nickel resists alkaline corrosion but gets rapidly dissolved in nitric acid and aqua. So the presence of carbon, arsenic, sulfur leads to the brittleness. Small amount of manganese render it more ductile where iron makes it hard. Now what is the use? So nickel is used in making the nickel steel, coin, German silver wires, catalyst for a moisture proof packaging. Nickel is widely used in alloying elements. Yes, in steel and cast iron, and electro deposited coating over steel to give corrosion protection. Nickel is also uh, used to form alloys with such element as copper, chromium, and it's had some alloys, as you know, the mantle metal, asti metal, and inconel. So you just read these alloys, and here we are completing our non-ferrous metal. So there is an exercise describe the manufacturing properties and usage of copper, aluminum, lead, then property and usage of tin, nickel, and zinc. See, uh, better that you should have the property. You should know the uh, properties and the use of the metal. That should be known to you, right? So that is a key. It is a key for the exam. Then there is some objective type of question that you should refer, and there is answer key is given. So first of all, you just read it, and then you check how much score you have. So thank you for having the listening of a lecture. So thank you very much.